topic.
Yeah. Should I start?
Yeah, you can start.
Hello, guys. I am Bhuvaneshwari. I am from Hyderabad. I'm currently studying in electronics and communications department, and I am interested in astrophysics and cosmology. So today I'm going to present about supernovae. Um, so let's get started.
Okay.
Yeah, today's presentation is about supernovae. Next. So the basic question is, what is supernovae? As we have discussed, stars are classified based on their size, shape, color, etc. Like blue giants, red giants, super giants, and our parent star, the sun, is a G2E star. So, despite of all these differences, most of them end as supernovae. Next slide, please. So, yeah, as we have as I've told, stars are categorized, and what actually supernova is a catastrophic star explosion that takes place at the end of the star's life. In a simple statement, it's a death of the star. So, supernova is the biggest explosion that humans have ever seen. Each blast is extremely bright and super powerful. They leave a radiant expression on the sky. So, on an average, how often supernova occur? On an average, every supernova, like a supernova, will occur about every 50 years in a galaxy, the size, which is at the size of the Milky Way. This stats is by NASA. So, putting in another way, a star explodes every second or so somewhere in the universe, and some of those aren't too far from Earth. Uh, Next slide, please. So, yeah, this is the life cycle of the star. So, we have the protostar. Then it forms a sun-like star. We have the main sequence stars, right? So sun-like stars, they form red giants, and at the end they form white dwarf, leaving planetary nebula, and then white dwarfs eventually become black dwarfs. And the other way, they become larger stars or giant stars, where both the larger stars and giant stars become red supergiants, and then they eventually become supernovae, and supernovae then becomes nebula, which in turn becomes a neutron star or black hole, depending on the mass of the stars. So, yeah, the most vital question is, what causes supernovae? So, yeah, I'm going to include few videos so that you'll get a brief idea what it is about. Yeah, we are going to see what is the type 1 supernova here. Sorry, it's the type 2 supernova, it's not type.
Hey, what was that? Oh, nothing much. Just the spectacular cataclysmic death throes of a star perhaps 20 times more massive than the sun. It's called a supernova. Since the sky first captivated him at age 13, Michael Schwartz has been probing the universe. But it hasn't always been with a telescope. In his early career, Michael worked to unravel the story of how human beings got to be so darn creative and smart. Smart enough to begin to understand how their universe is put together. And smart enough to realize that it's flying apart. A successful business during the gold rush days of computer software gave Michael the financial means to build an automated observatory that tracks the brightest lights of this expanding cosmos. But what exactly are these huge explosive stars whose images Michael seeks each night?
Supernovae occur because at the end of their lifetimes, stars do not have energy to keep their mass, their body up. There is no more production of energy in the center of the star by nuclear burning, and stars have to contract and collapse. The bigger the mass, the more catastrophic the event is going to be.
Big stars, say 8 times more massive than our sun, will try to fuse heavier and heavier elements. Hydrogen to helium, helium to carbon, and so on.
And then, all of a sudden, it gets to iron. And iron is a problem. When a star tries to fuse iron, iron actually takes energy in when it fuses. So if you fuse iron, you're actually absorbing energy instead of letting energy out to support the star. That's bad. A star will die a couple milliseconds after it begins to form iron in its core, because now, instead of energy supporting all that gravity, it's taking it up and the star collapses. And this collapse is the precursor to what we call a supernova explosion.
The entire core of the star implodes, releasing an enormous blast of gravity waves, neutrinos, electromagnetic radiation.
The whole outer envelope is thrown into space at speeds of 10,000 miles per second. And this is, when the star is a supernova, it can outshine an entire galaxy when this explosion happens.
That is also seen across enormous distances of space. We can see these things a billion light years or more away with the Hubble telescope.
The core that's left is an object that is a mass roughly that of the sun, but a radius of only 6 miles. This is how dense this object is. That's the object we call a neutron star.
A supernova is the ultimate pressure cooker. And when the lid blows off, some amazing ingredients are served across the sky. The essential elements, in fact, for just about everyone and everything you know.
So, for example, gold. I always like to think of the gold in my wedding ring. Gold is a more complex element than iron. It's actually a heavier element than iron. And the only thing in the universe that forms a gold atom is a supernova explosion. So when you think about things like gold or silver, or in fact even the iron in your blood, that iron was formed the very instant a star died.
So it's both a death and a rebirth for stars and for the universe.
Hope you all understood. So we'll have a recap on what they have said. So that's not the thing. Yeah, I just kept it for. I need the next slide.
Okay, okay.
Yeah. So a supernova is something occurs only if there are changes or more appropriately chaos in the core of the star. So this happens in 2 different ways, and the 2 will result in a supernova explosion. So what we have saw is the second type, that is type 2 supernovae, where the explosion takes place at the end of the star state. So to recap, every star that goes through a process called nuclear fusion, where the basic elements hydrogen fuses with itself releasing a huge amount of energy, and it forms helium, then forms carbon. It goes on fusing with the elements, forming higher and higher elements like iron. So this nuclear energy flowing outwards prevents the star from collapsing due to the star's gravity acting inwards. So this we'll look at in deeper further. So this helps the star to stay alive. The outward pressure and the inward pressure formed by the nuclear force and the gravitational force helps the star to stay alive. So when a star tries to fuse iron, it takes energy or absorbs energy rather than emitting or radiating out to support the star. So now instead of opposing the star's gravity, uh, the ion is taking or observing the energy. So once the star core surpasses a certain mass, that is the Chandrasekhar limit, the star begins to implode. For this reason, these supernovas are also called as core collapse supernovae. The entire core of the star implodes, releasing a violent blast of gravitational waves, neutrinos, electromagnetic waves, with the speed of 10,000 miles per second, as explained in the video, and resulting in a monstrous explosion, which we call as a supernova. I hope you all understood this. So, yeah, we were talking about implosion and explosion. It's a little deep concept, and I thought like everyone should understand what is it. Yeah. So the innermost, yeah. So this is the core. This is the core of the star. Yeah. So as we can see in the diagram, core gets scrunched into enormous balls of neutrinos when it surpasses the Chandrasekhar limit. So yeah, there are neutrinos and neutrons and protons inside the core, which gets gathered inside, uh, and it is a dense collection of iron, nickel, cobalt, and other elements. They get forcefully scrunched, and when they fuse into enormous balls of neutron, the layers atop they also collapse but rebound against the dense proto-neutron star, which we can see in the diagram um, in the core, which triggers an incredible burst of nuclear fusion. So yeah, this happens there. So as the layers pile up, they rebound, creating a fusion or like fusion waves of fusion, radiation, and pressure that comes out of the star. The more appropriate word is the cascade out of the star. These fusion reactions takes place over a time scale of approximately 10 seconds, and the overwhelming majority of this energy is carried away in the form of neutrinos, which hardly ever interact with the matter. Yeah, I think you all are getting this. This is a little more into the particle physics. So the remaining energy, uh, like the energy carrying particles, like including the neutrinos, nuclei, electrons, and photons, even with the intense amount of energy imparted to them, they have to have their energy cascade and propagated through the entire outer layer of the stars, which means like they rebounds to the core and they come out of the star surface. The last dotted lines, which is in the diagram, so they come out of the uh, outer layers of the star. So as a result, we can say that neutrinos are the first signal which we can receive on the earth, and yeah, we can detect um, like there's a super in the universe at present. So yeah, this is illusion, like this is analogy actually. Yeah, fill tank, we have the thrust by the water, and there's a pressure from outer surface, that is the normal force which acts. So this helps the star to stay alive. So when this force exhausts, there's nothing left, so the outer force becomes more. And yeah, so that so that forces, that pressures the tank to, yeah, I hope you got what I'm saying. So the next picture is, yeah, implosion and explosion. Yeah, implosion is pressure inwards. That is due to the top layers, what I was talking about in the before slide. And the bounce is the explosion, supernova. Yeah. So next slide, please. Yeah. So yeah, now we're going to talk about type 1 supernovae, where the explosion takes place in the binary star system. Yeah, binary star system consists of two stars orbiting around their barycenter. Uh, they may be normal stars or white dwarfs. Yeah, they can. But these supernovae takes place when there is at least a white dwarf present there. So here we have two other classifications: a single degenerate progenitor and the double degenerate progenitor. Next slide, please. Yeah, this single degenerate progenitor. So here, a binary in this model, the white dwarfs accrete mass. There's a single white dwarf and a giant companion. So here, white dwarf accretes the matter. In this case, if it is not unreasonable to expect hydrogen rich materials. Actually, if we see the chart here, so there are two normal stars and they are in binary pair. One becomes a giant star, and then it engulfs the other star with its matter. So the next one, the secondary lighter star and core of the giant star spiral towards within a common envelope. So it releases all the matter, and yeah, they move around their barycenter with the matter. So the common envelope is ejected while the separation between the core and the secondary star decreases. The remaining core of the giant collapses and becomes a white dwarf. Yeah, the star becomes the star which falls under. Sorry, I'm a little nervous. The star which comes under the main sequence star, it becomes a white dwarf. And yeah, here comes the real story. Yeah, the uh, it actually, the other companion is the red giant. So it will start swelling and spilling gas as a normal red giant does. I cannot see.
1 second. Yeah.
Yeah. So the white dwarf, yeah. So after the white dwarf takes the matter. In simple words, it takes the matter from the other star, and it increases until it reaches a critical mass. What that's called as Chandrasekhar limit, and it explodes. So causing the companion to be ejected away. So this engulfment of matter causes the supernovae explosion. So we
Okay.
have a video
Shall I play that?
beside to, yeah, just to illustrate what actually happens. I don't think so. It has any sound. Yeah, I hope you all got a idea what happens there. So this is about the single degenerate progenitor, and it is estimated that these single degenerate progenitor account for no more than 20% of type 1a supernovae. So next slide.
Yeah, 1 minute. Yeah, this is pretty interesting. Yeah, I think it's a good idea to go a bit more in detail into type 1A supernovae, so we'll do that later. Yeah, you can continue.
Yeah. So in double degenerate stars, we have two white dwarfs. Whose combined mass exceeds the Chandrasekhar limit, what we were talking, like it surpasses the limit. So this results in a merger, and this is called as super Chandrasekhar mass white dwarf. When we have two white dwarfs like that, so in such case, the total mass would not be constrained and constrained by the Chandrasekhar limit. So in this model, the white dwarf merges with another carbon oxygen white dwarf companion, uh, and results in a supernovae. So like I forgot to tell you one thing. In single degenerate star, we have hydrogen spectrum, hydrogen lines in the spectrum, and because we have a red giant there, and we have elements of hydrogen, which and we get the hydrogen lines. And here we don't have anything because there are two white dwarfs and there's no hydrogen left in the stars. Can I have the link, please, to show the illustration?
Okay, you want me to open that link?
Yeah. Yeah, hope you all understood what it is about. So, moving on to the next slide. Uh, yeah, the history and the observations. So, when did we find the supernovae and what did we discover till now? Yeah. So, these supernovae were detected long before the invention of the telescope. The oldest recorded supernovae is RCW86, which Chinese astronomers they have written in their recordings in 18 AD 1805. So this their records show that this is a guest star that stayed in the sky for 8 months, and it's according to NASA. Before the early 17th century, we had 7 recorded supernovae in according to Encyclopedia Britannica. So what we know today as the Crab Nebula is the most famous of all the supernovae. Chinese, Korean astronomers recorded their star explosions in 15 or like 1054, and southern western Native Americans also may have seen it because this is said through their rock paintings and rock carvings. The supernova that formed the Crab Nebula was so bright that astronomers could see it during the day in those days. And the term supernovae was is termed by Walter Brande and Fritz Zwicky at the Mount Wilson Observatory, which means a great explosion, and it was to address SN 1885A supernovae. So one of the most famous supernovae is SN 1987, which is still visible in the night sky. In the night sky for all, it's visible for more than 30 years. So yeah, do check that. So Can we have the next slide? Yeah, these are a few of the historical supernovae: SN1006, Tychon's SN, and Kepler's SN. Yeah, most of the supernovae were visible in the morning sky also, because they were so bright, and yeah, they were more brighter than the sun. We are expecting a supernova. We were expecting a supernova. Yeah, we'll go to the next slide. We will have the discussion about that in the next slide. Yeah, how and why scientists study supernova? Yeah, this is the most important question. Why are we studying? So, going how to study? We study supernovae through many telescopes. Sent one is the Hubble telescope. Then, yeah, we use X-rays, Naxxatra X-ray Observatory, and NU star, that is nuclear spectroscopic telescope array, and we study through gamma rays, and we study through UV rays. So for the we are going through detailed explanation of how we capture images through gamma rays, because I think it's more efficient than any other X-ray or UV rays. And yeah, we have an explanation in the video. Can you play the video? It is more detailed here.
About 2 or 3 times a century, a massive star in our galaxy explodes. The star's core may survive as a neutron star or a black hole, but the rest of it rushes into space as a swiftly expanding debris behind a powerful shockwave. As the supernova remnant grows, it sweeps up interstellar gas and gradually decelerates. Yet even thousands of years later, its imprint on the galaxy remains impressive. Exploding stars in their orbits have long been suspected of producing.
Sorry, what happened?
Yeah, it is like resonating.
Resonating. So it's like you're hearing some echo.
Yeah, we can hear it twice. Yeah. Now I think it will be okay.
Producing cosmic rays, some of the fastest matter in the universe. Where and how these protons, electrons, and atomic nuclei are boosted to such high speeds has been an enduring mystery. Now, observations of 2 supernova remnants by NASA's Fermi Gamma Ray Space Telescope provide new insights. Because cosmic rays carry electric charge, their direction changes as they travel through magnetic fields. By the time the particles reach us, their paths are completely scrambled. We can't trace them back to their sources. So scientists must locate their origins by indirect means, which is where Fermi comes in. The interaction of high-energy particles with light and ordinary matter can produce gamma rays, the most powerful form of light. Unlike cosmic rays, gamma rays travel to us straight from their sources. In 1949, physicist Enrico Fermi worked out how what he called magnetized clouds could accelerate cosmic rays. Later studies showed that a variant of his method, called Fermi acceleration, worked especially well in supernova remnants. Confined by a magnetic field, high-energy particles move around randomly. Sometimes they cross the shockwave. With each round trip, they gain about 1% of their original energy. After dozens to hundreds of crossings, the particle is moving near the speed of light and is finally able to escape. If the supernova remnant resides near a dense molecular cloud, some of those escaping cosmic rays may strike the gas and produce gamma rays. But electrons and protons make gamma rays in different ways. Cosmic ray electrons do so when they're deflected by passing near the nucleus of an atom. Accelerated protons may collide with an ordinary proton and produce a short-lived particle called a neutral pion. These pions quickly decay into a pair of gamma rays. At their brightest, both types of emission look very similar. Only with sensitive measurements at lower gamma ray energies can scientists determine which process is responsible. Now, Fermi observations have done just that. They conclusively show these supernova remnants are accelerating protons. When they strike protons in nearby molecular clouds, they produce pions, and ultimately, the gamma ray emission Fermi sees. NASA's Fermi has detected gamma rays from many more supernova remnants, but the jury is still out on whether accelerated protons are always responsible and what their maximum energies may be. Nevertheless, the Fermi team has taken a major step, a century after the discovery of cosmic rays, in establishing just where they arise. Something that would satisfy, but certainly not surprise, the original Fermi.
Yeah, so the main thing is here is to capture that gamma rays travel straight and they don't get deflected because they have high energy, and that can be easily caught by the telescope. Like we can find it more uh, before than the other techniques. Today we have it today, and there are also neutrino detectors, but it takes a lot of time to detect. Through where we have a nuclear neutrino detector in Japan. So yeah, going to the next slide. Why do scientists study supernovae? So what is the reason? What uh, insights does supernovae give us? What does it show us? So yeah, a supernovae it burns for a short period of time, but it can tell a lot about the universe. So one thing is that yeah, it helps in the understanding and working of the universe, how it works, how it's expanding. So this explosion, yeah, so this explosion consists of several elements with which we are made of. Thus, help in understanding our existence. The scientist said in the video, the astrophysicist who explained in the video, like gold and even the iron and the blood, yeah, they are formed through supernovae. So next, it helps in the understanding of the dark energy and is dominant in today's universe, which in turn helps us in understanding the expansion of the Earth. Type 1 is supernovae are standard candles which are used in finding distances between cosmological objects. Yeah, this is one of the way we use Cepheid variables, and yeah, we also use type 1 is supernovae to find the distances between stars. So it also played a major role in providing the theory of neutrinos, because neutrino explosion, yeah, first we get the first signal of neutrinos through supernovae, right? So yeah, many of the scientists claim this supernova explosion, and their studies help many of the scientists to prove the theory of supernovas, and it led to a better understanding of science today. Yeah, so yeah, the next slide. Yeah, nowadays this Beetlejuice is in news. Many of us have heard it, I guess. So yeah, there's a controversy that it explodes or not, and we have a lot of things going on nowadays. And in 2020, we have got a different result of this of the data collected. So yeah, we'll see it in the next slide. What happened? Yeah. So this Betelgeuse is in the arm of Orion constellation. It's a mature red giant. Sorry, it's a supergiant actually, red supergiant. In October 2019, there was dimming of the supergiant, and this has led to speculations that supernovae can be imminent. Now there is a sign that its brightness is perking up. Temperature inside the Betelgeuse core is so hot that the helium here has begun to fuse into carbon. Betelgeuse's usual pulsation cycle is 420 days. Scientists list the probabilities as first thing, it can be caused by variations in the star size, and second thing, a possibility is that the star has been obscured. That is, the star like Betelgeuse periodically shed mass from their surface, which condenses into dust around the star. So this would effectively block our view. They admit that they have a very little idea about what a star will do in its final days or weeks actually before it explodes. So they have the best guess according to its life cycle, as it will die in 100,000 years from now. They have this guess after having a lot of discussion and the data analysis. So yeah, there's no probability of having it in coming years from now, like not in 5 or 6 years, but it takes 100,000 years. So yes, this is happening. This is the most spread news nowadays. Yeah. So yeah, every star every collapse become a super, like every core collapse become a supernova? No, it doesn't become a supernova. It many of the stars become stellar. They become yeah, a failed supernovae. It is a astronomical event where stars suddenly brightens at its early stage of supernova, but it does not increase to the increase its brightness as expected in a general supernova. So we have a subcategory. This can come under the subcategory of supernova imposters, and so these failed supernovae are thought to create uh, supernova imposters. Sorry, thought to create stellar black holes by collapsing of a red supergiant star in its early stages of supernova. So when the star can no longer support itself, the core collapse completely takes place, forming a stellar mass black hole, and consumes the whole supernova without having the massive explosion. So this takes place, and this we call it as a failed supernova. For a distant supernova, for a distant observer, the red supergiant star will seem to wink out of the existence with a little or no flare. The observed instances of these disappearances seem to involve a supergiant stars with mass more than 17 solar masses. So yeah, this is what a failed supernova is. It forms directly into it forms a stellar black hole directly without having a great explosion, what we call a supernova. The next slide, please. Yeah. So this is yeah, the shock wave stalls, more gas falls onto the neutron stars. It collapses to form a black hole. No explosion visible, just neutrinos. Yeah, it releases just neutrinos. Yeah, we have come to the end. So this is an illustration of the crab explosion. Yeah, it's beautiful, right?
Yes. That was nice. Do you have any other slides left? Okay. Yeah, you can
Yeah.
summarize that if you want.
So I've presented. So what we have discussed is we have understood what is a supernovae, what causes supernovae, what is implosion and explosion, what is the difference between them, and what is the reason for implosion and explosion in the supernovae, in the process of supernovae, the history and observations, how and why scientists study supernovae, and the most famous Betelgeuse, will it explode or not? What is a failed supernova? And we have saw a stimulated video of crab supernova explosion. Thank you.
Okay. That was excellent. Thank you so much. That was like super informative. So I think, I mean, even personally, like for you to have put all this information together, you must have learned so much, right? In the process.
Yeah.
Yeah. So that's like that's the best part because you personally work through all of this information and put it together. So let's hear some maybe questions or comments from anybody else here. Anything else you want to bring up regarding supernova? So we will be taking the, the usual journey of the stellar evolution, right from like the protostar all the way to black holes. So in that process, we'll understand why the supernova explosion is happening in the first place, like in more clarity. But for now, from whatever insights you've gathered from today's talk, would you like to summarize, or anybody else would like to ask any questions?
Yeah,
Aditya, did anything not make sense? Or did you find anything specifically hard to understand?
No, but I have a doubt. Um,
Okay.
so, the supernova that created Crab Nebula, what kind of supernebula? No, supernova was it? Type A or something like that.
Mm-hmm.
okay. We'll just type in internet and see.
That is just type 2, right? Because it's not a type 1A, I'm guessing. Uh, because it
Yeah,
must
I
have
guess it is
occurred out of
type
the death of a star, the final stages
star.
of a star. Yeah. So, Bhuvana, do you want to summarize the main difference between type 1A and type 2?
Yeah. So the type 1A supernova, it'll occur uh, when a star dies. Actually, when a star comes to its final stages, the we know that nuclear fusion takes place in every star, like that of our sun, and it emits hydrogen. And yeah, as I've discussed, like the filled tank and the outer pressure, so the filled water thrust, it helps you to withstand the outer pressure, and yeah, then the star lives. As the time passes, the hydrogen, yeah, so the hydrogen exhausts, and there's nothing to fuse more. And yeah, while when we reach iron, as explained, it absorbs energy rather than emitting. So yeah, it helps the gravity to collapse the core. And yeah, so the collapse when the core collapses, there's an implosion and there's an explosion as a rebound effect. So yeah, the explosion what we see is a supernova. That is type 1 supernova. Type 2 supernova, actually, sorry. Type 2 supernova. And type 1 supernova is when a white dwarf or a red giant or two white dwarfs, they merge together and they
Mm,
form a big explosion. So this is what happens there.
correct. So there's a lot of different things we can study here. Like when it comes to type 1A, I think first of all, why is it used as a distance measurement technique? Like type 1A is one of the ways we measure distances in astronomical scales. And why is that possible? And second question is, what are the different kinds within type 1A, right? There are basically, you're talking about mergers. So I think this is a very interesting field to explore. Like you have these, for example, white hole. You have a white dwarf and a red giant revolving around each other. Sometimes you have two white dwarfs. So what are the kind of gravitational plays that are happening over here? So I think that's also an interesting thing. And maybe we can also explore what happens if two neutron stars merge, right? Like we haven't explored that, but whether or not it produces a supernova, does it produce some other kind of astrophysical event? I don't know. So maybe I'll put that up. We do have a upcoming project for which we'll be selecting a few people from this group who can take it forward, and that will be regarding neutron star mergers. And basically it will be regarding the lifetime of neutron star mergers, and we know that mostly when they merge they turn into black holes, right? So it's not really like white dwarfs will turn into maybe create a supernova explosion, but when neutron stars merge, it's a much stronger event with a lot of more gravitation involved, so usually ending up in a black hole. So let's stick to supernova for now. I think there are more types that we can explore, and I think this week's question should be more about the different kinds and what masses the original stars have to be in order to become those different kinds of supernova, right? So, for example, if it is within 100 stellar masses, what happens? What happens if it is above, like, that what if it is 1,000 solar masses, what happens then? So there are different possibilities, and I think that can be a little homework. So meanwhile, did Vishal have a question?
Yes, I do.
Yeah.
What triggers the death of a star? Like I know, like it run out of fuel and collapses into itself, but what triggers it in the core?
What happens in the core, right?
Yeah.
So, yeah, do you want to answer that? I think we will definitely be looking at that in detail, but you need to also understand the cycle of fusion that happens, right? So, stars go from one step to the next step of fusion. Goes from first fusing hydrogen, then helium is formed, then it goes into the next step in order to create heavier and heavier elements. But there is also an interplay of two things here, which is important to note, Bone. I'll just mention this, which is basically, she also mentioned it, it's basically the play of gravity and pressure. These are two things that are in constant tug of war in every single star out there. Okay, even from the beginning stages of star development, there are two things. There is hydrostatic power, or just pressure. Sorry, this pressure is trying to push the star out, and gravity is trying to pull the star in. So these are two opposing, conflicting forces which are constantly fighting each other. So in every step, the efficiency of fusion decides whether or not the star is going to survive and be stable. And that is why larger, bigger stars, they actually last for a much lesser number of years. Their lifetime is less when compared to medium-sized or small-sized stars, right? So the stability of the star really depends on whether it can withhold the pressure and fight against it and keep itself together. But in a supernova, the efficiency of fusion comes down when it hits ion. It's no longer efficient enough to fight pressure, the pressure that is pushing the star outward. So at that point, there is on one hand, there is a collapse. On the other hand, there is a massive explosion of these outer layers, which is pushing a lot of mass and energy outward. And it gives it such a kick that it goes, like she said, at 10,000 miles per second speed. It's like an insanely high velocity for such a huge system to just, accelerate outward. And this in turn produces a bunch of stuff like cosmic rays and neutrinos and gamma radiation and so on. So so that is what is happening. And in when it comes to doing the math of it, it will first of all involve the fusion energy calculations, and other than that, calculating how gravity and pressure are kind of balancing each other out. So those are the few aspects or parameters we'll be working with when we do the measurement. When we try to predict when will the star go supernova, when will it explode, then these are some of the parameters you want to work with. So Bhuvana, do you want to add something to that answer and what is happening in the interiors?
Yeah, as I've explained, and the explode. Yeah, the basic thing is what Sitara said. Yeah, that fusion happens. Why implode and explosion takes place, I've discussed. If you want, I can discuss it again.
Yeah, so not the fusion itself, maybe just so what happens at the moment, like they talk about how ion is kind of fatal to the star almost. And that's how really dramatic it is, because we're not talking about days or years, we're talking about seconds. Like when the supernova happens, it's a matter of like 5 to 10 seconds when
Yeah, it
ion
happens
starts.
in 10 seconds.
Yeah, and the whole thing goes crazy and it becomes a catastrophic event in a matter of seconds. And all these heavier elements like gold and silver and so on are manufactured in a matter of those like milliseconds actually. And and often this will create a nursery and a space where new and younger stars can form. Like in fact, our star will never go supernova, it's going to go red giant, right? It's a medium sized star, but therefore it must have had a parent star of its own. So our sun had some larger star go supernova in order for it to be born. So yeah.
Yeah, or else it can become a white dwarf and merge with some other star. Will that happen?
Yeah, that's probably a possibility, but maybe that happens with binary star systems. I'm not sure if, like, yeah, maybe if there is another white dwarf and the gravity plays out on a larger scale of time, that could probably happen. Yes, but otherwise, yeah, it will go white dwarf for sure after red giant. And yeah, unless there is some other white dwarf out there, it will slowly evaporate. In fact, there is a interesting video about white dwarfs. They are very, very interesting, and these are objects that will outlive almost every other kind of object in the universe. We are talking like trillions of years down the line, where white dwarfs will still kind of have this soft glow, and they will still kind of be burning, and they'll be the last things to be last luminous objects in the universe after everything else burns out. So yeah.
Yeah.
Hmm.
Excuse me, I have doubt.
Yeah.
Okay. So when a supernova happens, does it explodes evenly in all places, or does it has some increase in pressure at some places, or something like that?
Yeah, do you have any answer to that, Bhuvana? That's a
Can
good
he
question.
reframe the question? I did not get
Like,
you.
is it uniform explosion is what he's asking. Like, does it, you know, explode out uniformly or homogeneously in all directions, or is it non-uniform?
Okay. Yeah, it doesn't explode uniformly, not as uniformly as weakest, but in data analysis, we take it as we take it uniformly, but actually the pressures differ a meter from. Yeah, I've gone through this. Yeah, the pressure differs. Yeah, the pressure differs because the rebounds which takes place inside when the layers are formed, they don't form. They don't come and bounce on the proton neutron star core uniformly. So they come out like not homogenetically. Like there's a slight difference, but yeah, you can take it as a homogeneous thing if you are in a data analysis thing. Yeah, if you are analyzing some data or
Okay,
something like
so
that.
I think what you're trying to say is you can make an assumption of